Hello, everyone. Let's begin by introducing one of the fundamental concepts in predictive analytics, linear regression. In today's session, we will explore the simple linear regression model in more detail, looking at the formula, assumptions, how to interpret coefficients, and where this method is most effective. Let's get started. Linear regression is a statistical method that helps us understand the relationship between a dependent variable and one or more independent variables. In simple terms, we try to draw the best-fitting straight line through our data to make predictions or uncover patterns. It's one of the foundational tools used in statistics and machine learning because of its simplicity and wide application. Purpose and use. The primary goal is to predict or estimate the value of the dependent variable. Our main objective with linear regression is prediction. We use known values of independent variables to estimate the value of something we care about, like predicting house prices based on size and location. Helps identify trends, patterns, and correlations in data. This model is also useful for discovering trends. For example, we might use it to identify whether there's a consistent increase in sales based on advertising spend. Why is it important? Easy to understand and interpret. One of the best things about linear regression is its simplicity. Even someone with limited statistical knowledge can grasp the idea of a line showing a trend. Serves as a baseline model in predictive modeling. In machine learning, we often start with linear regression as our baseline. If a complex model doesn't perform much better than this, we stick to linear regression. Used in both descriptive and inferential analytics. Linear regression serves both to describe relationships in our data and to make broader predictions or inferences about a population from sample data. Let's now compare simple and multiple linear regression side by side using this table. This will help you clearly see where they differ and when to use each. There are main two types of regressions: simple linear regression and multiple linear regression. Here are the equations. For simple linear regression, y equals beta naught plus beta 1 times x plus an error term. For multiple linear regression, we add more terms for each additional x variable up to beta and xn. Simple linear regression involves only one independent variable, x, and one dependent variable, y. In contrast, multiple linear regression involves two or more independent variables. With simple linear regression, we also examine the strength and direction of the linear relationship between the two variables. Multiple linear regression enables us to assess the combined effect of different predictors, which is crucial for analyzing real-life problems where many factors play a role. For instance, predicting a student's score based solely on hours studied is a use case of simple linear regression. Meanwhile, predicting house prices using multiple variables like square footage, number of rooms, and location is an example of multiple linear regression. Let's now compare simple and multiple linear regression side by side using a table. This will help you clearly see where they differ and when to use each. Number of predictors. In simple linear regression, we use only one independent variable to predict the outcome. In contrast, multiple linear regression uses two or more predictors, making it more suitable for complex real-world problems. Equation format. The simple equation is y equals beta naught plus beta 1 x plus error term, a straight line relationship. Multiple regression expands this to y equals beta naught plus beta 1 x 1 plus beta 2 x 2 plus, so on plus error term, adding terms for each predictor. Interpretation. Simple regression is easy to interpret. We just look at how one variable affects the outcome. Multiple regression is more complex and may involve interactions between variables, meaning the effect of one factor can depend on another. Use case example. Simple regression might be used to predict someone's weight from their height. With multiple regression, we might predict salary by considering factors like education, work experience, and job location all at once. Visualization. Simple regression is visualized as a straight 2D line on a graph. Multiple regression can be visualized as a plane or multidimensional surface, like the 3D plot you see here, combining experience and education to predict salary. In linear regression, certain assumptions must be met to ensure valid and reliable results. These include conditions about the relationship, residuals, variance, and predictor independence, especially in multiple regression. 1. Linearity. First, we assume a linear relationship between the independent and dependent variables. This means changes in the predictor should lead to proportional changes in the outcome. To check this, we use scatter plots or partial regression plots to see if the data points roughly form a straight line. 2. Independence of errors. Next, the residuals or errors must be independent of each other. This means there should be no pattern or sequence in the error terms. For time series data, we often check this using the Durbin-Watson test to ensure there's no autocorrelation. 3. Homoscedasticity, constant variance of errors. Finally, we assume that residuals have constant variance across all values of the independent variables. If the spread of residuals changes, for example forming a funnel shape, that violates this assumption. We check for this by plotting residuals against predicted values. 4. Normal distribution of errors. The fourth assumption is that the residuals, or the differences between observed and predicted values, should follow a normal distribution. This is particularly important for making valid statistical inferences like p-values and confidence intervals. We can check this using a histogram or a QQ plot of the residuals to see if they follow a bell-shaped curve. 5. No multilinearity for multiple linear regression. This assumption applies specifically to multiple linear regression. It states that independent variables should not be too highly correlated with each other. If they are, it leads to multilinearity, which inflates standard errors and makes the coefficient estimates unstable and unreliable. To detect this, we use tools like the variance inflation factor, VIF, or a correlation matrix. This slide shows the basic formula used in simple linear regression. This formula helps us predict the value of a dependent variable, y hat, based on a single independent variable x. Y hat. This represents the predicted value of the outcome we're trying to estimate. Beta is 0. This is the intercept. It tells us the expected value of y when x is 0, basically where the line crosses the y-axis. Beta 1. This is the slope of the line. It indicates how much y changes for every 1 unit increase in x. X. This is our independent variable, the input or predictor that influences the outcome. Epsilon. This is the error term, representing the difference between actual and predicted values, essentially the noise the model can't explain. This slide shows a practical example of how simple linear regression works. We're using a regression equation to predict a student's test score based on how many hours they study. The equation we're using is y hat equals 40 plus 5x. Here, 40 is the intercept, the expected test score if no studying is done. 5 is the slope. For every additional hour studied, the score increases by 5 points. Let's say a student studies for 8 hours. We plug 8 into the equation. Y hat equals 40 plus 5 multiplied by 8. Y hat equals 40 plus 40 is equal to 80. So the predicted test score is 80. Based on this model, we can say that a student who studies for 8 hours is predicted to score 80 on the test. This kind of prediction helps us understand the influence of study time on performance, a perfect example of how linear regression is applied. The least squares method is used to fit the best possible straight line through a dataset by minimizing the sum of squared residuals. This helps ensure that the predictions our model makes are as close as possible to the actual values. The main objective here is to find the best fitting line through our data points. We do this by minimizing the sum of squared residuals. In other words, we want the line that keeps the errors as small as possible. Residuals are simply the errors, the difference between what actually happened and what our model predicted. It's calculated as actual value minus predicted value. Here, you can see how each point has a vertical line down to the line of best fit. These lines represent residuals. The least squares method finds the line where the total length of these squared residuals is the smallest. Mathematical objective. Our mathematical goal is to minimize the sum of the squared differences between the actual and predicted values. Minimize sigma, e hat, superscript 2. This formula ensures we're reducing overall prediction error, where terms mean e is the actual observed value. E hat is the predicted value from our model. Sigma means we're summing this difference over all data points. Why minimize squares? We square the residuals to remove negative signs and prevent positive and negative errors from canceling out. Also, squaring exaggerates large errors, helping the model focus more on reducing those big mistakes and improving overall accuracy. Let's interpret each coefficients in regression equation. Beta note intercept. Let's start with the intercept, beta note. This represents the predicted value of y, the dependent variable, when x is 0. It serves as the baseline starting point for our regression line. For example, if no hours are studied, the intercept gives the predicted test score. Beta 1 slope. Next, beta 1 is the slope of the regression line. It tells us how much y is expected to change for each 1 unit increase in x. This gives us insight into the strength and direction of the relationship, whether x has a strong or weak influence on y. Sign of beta 1. The sign of a slope is just as important as its value. If beta 1 is positive, it means that as x increases, y also increases, a direct relationship. If beta 1 is negative, y decreases as x increases, an inverse relationship. Understanding this sign helps us make meaningful interpretations and business or policy decisions. Now, let's evaluate the model. R squared. R squared tells us how much of the variation in the dependent variable is explained by the independent variables in the model. It ranges from 0 to 1. The closer it is to 1, the better the model fits the data. Adjusted R squared. This is similar to R squared, but with an adjustment for the number of predictors used. It's especially helpful when comparing models. For instance, if you add a new variable, adjusted R squared will only increase if that variable truly improves the model. P-values. P-values test the significance of each coefficient in the model. A p-value below 0.05 typically indicates that the variable is a statistically significant predictor. This helps us decide which variables actually matter. F-statistic. The F-statistic assesses the overall significance of the model. A large F value with a low p-value suggests that the model, as a whole, is meaningful and better than a model with no predictors. Residual analysis and diagnostics. Plotting residuals. Residual plots help us check whether the assumptions of linear regression hold true. By comparing actual versus predicted values, we can see if the errors, residuals, are randomly scattered or follow a pattern. Nonlinearity. If the residuals show a curved pattern, it means the model may not be capturing the true relationship. A linear model may not be suitable, and we may need to consider polynomial regression or another approach. Outliers. Outliers appear as extreme points on the residual plot. They can distort the regression line and mislead our interpretation, so we must assess whether to keep or remove them. Heteroscedasticity. This means the spread of residuals is not constant across all levels of x. You'll see a funnel shape or increasing spread. It violates the assumption of constant variance and can affect model reliability. Normality of residuals. Residuals should follow a normal distribution for valid statistical inference. We can check this using histograms or QQ plots. If residuals deviate from the diagonal line in the QQ plot, it signals a problem. Now, let's talk about limitations of linear regression. Sensitive to outliers. Linear regression is highly affected by outliers. Even one extreme value can pull the regression line off course and give misleading predictions. That's why outlier detection is critical during analysis. Assumes linearity. This method assumes a straight-line relationship between the independent and dependent variables. If the actual relationship is curved or complex, the model won't perform well and predictions will be off. Poor performance with nonlinear data. Without transforming variables or using more advanced methods, linear regression fails to handle nonlinear trends. So it's not suitable for capturing curved or cyclical patterns in data. Multicollinearity in multiple regression. When independent variables are highly correlated, it causes multicollinearity. This inflates the standard errors, making it hard to determine which variable is actually influencing the outcome. Assumption dependent. Linear regression relies on key assumptions like linearity, homoscedasticity, independence, and normality. If these assumptions are violated, the results, including statistical tests, become unreliable. Thanks for watching. Today, we covered the essentials of linear regression, from the basic formula and assumptions to model fitting, interpretation, evaluation, and limitations. If you found this helpful, don't forget to like, subscribe, and hit the bell icon so you won't miss more videos like this.